This chapter explores negative feedback amplifiers, their structure, advantages, and stability concerns. Feedback is a fundamental concept in engineering, widely used to enhance system performance by trading gain for desirable properties like stability and predictability. The chapter details the mechanisms of feedback, the impact on amplifier performance, and the potential risks of instability. Given that electronic circuits are the backbone of modern technology, understanding feedback amplifiers is crucial for designing robust and reliable systems that function effectively across a range of conditions. Feedback occurs when a portion of an output signal is returned to the input. It can be either positive or negative. Negative feedback, the primary focus of this chapter, is used in amplifier design to desensitize gain, making it less sensitive to component variations. This is particularly beneficial in manufacturing, where variations in transistor parameters could otherwise cause large discrepancies in circuit behavior. It also reduces distortion, ensuring a more linear relationship between input and output. In applications such as audio amplifiers and communication systems, distortion reduction is vital to preserving signal fidelity. Another advantage is its ability to reduce noise, minimizing unwanted signals that could interfere with performance. For instance, in medical imaging devices such as MRI scanners, noise reduction is critical to obtaining clear and accurate images. Additionally, negative feedback can control input and output resistances, adjusting them for better circuit integration. It also extends the bandwidth of an amplifier, improving its frequency response. This is particularly useful in high-speed data transmission, where a wider bandwidth enables the processing of faster signals with minimal degradation. While negative feedback provides these benefits, it comes at the cost of reduced gain. The chapter explains how engineers can strategically design circuits to achieve the best trade-offs, ensuring optimal performance while maintaining stability and reliability. A feedback amplifier consists of a basic amplifier with an open-loop gain, a feedback network that extracts part of the output and returns it to the input, a mixing circuit that combines the feedback and input signals, and a loop gain, which determines feedback effectiveness. The chapter details how these elements interact and how feedback alters amplifier behavior. Feedback amplifiers are classified based on how the input and output signals are sampled and returned. The four main topologies are voltage-voltage feedback, used in voltage amplifiers, current voltage feedback, used in transimpedance amplifiers, voltage-current feedback, used in transconductance amplifiers, and current-current feedback, used in current amplifiers. Understanding these classifications is crucial when designing electronic systems. For example, transimpedance amplifiers are extensively used in photodetectors, such as those in fiber optic communication systems, where they convert small current signals into usable voltage signals. Similarly, voltage amplifiers with negative feedback are essential in high-quality audio amplifiers, ensuring consistent sound levels without excessive distortion. Negative feedback modifies the gain from an open-loop value to a closed-loop value. The formula governing this behavior shows that when the loop gain is large, the closed-loop gain primarily depends on the feedback network rather than the open-loop gain. This results in a more predictable, stable system. However, feedback can also introduce stability concerns if improperly designed. The chapter covers stability analysis and corrective measures. In practical applications, stability is especially important in power electronics, such as switch-mode power supplies, where unstable feedback can lead to voltage oscillations, potentially damaging connected devices. Engineers designing power systems must ensure that feedback circuits are stable to prevent erratic behavior. Negative feedback provides several key benefits. It desensitizes gain, meaning that the sensitivity of gain to parameter variations decreases, enhancing circuit reliability. This is particularly useful in industrial control systems, where stable gain ensures precise control of machinery. It extends bandwidth since feedback increases the bandwidth by the same factor that it reduces gain, leading to a gain-bandwidth trade-off that engineers can leverage for high-speed applications. High-speed operational amplifiers used in radar and high-frequency communication systems depend on bandwidth extension to maintain signal integrity. It reduces nonlinear distortion by lowering signal amplitudes at active device terminals, improving linearity, and reducing harmonic distortion. In broadcasting equipment, reducing distortion is crucial for delivering clear, high-fidelity audio and video signals. Feedback also reduces the impact of noise from active components and suppresses interference, improving signal integrity if the interference source is outside the loop. This is particularly important in satellite communication, where signals are weak and highly susceptible to noise and interference from other sources. A key challenge in feedback systems is stability. If the loop gain becomes negative at high frequencies, the amplifier can oscillate. The chapter explains how Bode plots and Nyquist criteria can be used to assess stability. It introduces the concept of phase margin as a measure of stability and describes compensation techniques such as lead-lag networks to prevent oscillations. In real-world applications, ensuring stability is critical in automotive electronics, where electronic control units, ECUs, rely on stable feedback circuits to regulate fuel injection, braking systems, and engine performance. Unstable feedback in these systems could lead to erratic vehicle behavior, posing safety risks. The principles of stability analysis outlined in this chapter equip engineers with the knowledge to design circuits that perform reliably under various conditions. Negative feedback is fundamental in many engineering applications. It is widely used in operational amplifiers for signal processing and control systems, in audio amplifiers to ensure high-fidelity sound reproduction, in voltage regulators to provide stable power supplies, and in communication systems to enhance signal quality in transmitters and receivers. In biomedical applications, feedback circuits are integral to devices like pacemakers, ensuring that they provide a consistent and appropriate heart rate response. In robotics, negative feedback is used in motor controllers to maintain precise speed and positioning, allowing for smooth and efficient robotic movement. In aerospace engineering, feedback systems are essential in flight control systems, where they help maintain aircraft stability and responsiveness under varying flight conditions. This chapter provides a thorough understanding of negative feedback, equipping engineers with the tools to design stable, high-performance amplifiers. The concepts covered have broad applications in modern electronics, ensuring reliability and efficiency in 21st century technology. By mastering the principles of negative feedback, engineers can develop circuits that not only perform optimally, but also contribute to advancements in industries ranging from telecommunications to healthcare and automation. This knowledge is essential for creating innovative solutions that address the growing demands of an increasingly digital and interconnected world. Thanks for tuning in. Be sure to subscribe for more chapter coverage. I will see you on the next one.